Hi all, today I will present my paper titled Fault Detection and Diagnosis in Photovoltaic Systems through IV Curve Analysis, presented by Batulis Diab and Bashir. First, we will give a brief introduction about PV systems and propose our technique and using and verify it using through simulation results using simulating, and finally conclusion and perspective will be presented. Introduction. The energy security, the need of clean energy, the attempt to reduce emission of CO2 gas. All these push organizations to reinforce renewable energy, especially the PV. While PV systems have many advantages, they are subject to various forces that can cause fire risk, reduce the efficiency, and degrade the panel. In UK domestic PV systems, the annual energy loss due to defects in PV systems is estimated to be up to 18.9%. So we are in desperate need to advance fault detection and diagnosis techniques to detect faults in PV systems, and this is our objective. PV system overview. The photovoltaic cell is the elemental component of the PV generator that converts solar energy into electrical energy. PV cells are grouped together in order to form PV modules, which are combined in series and or in parallel to provide the desired output power. The PV cell has two characteristics, the IV curve and the PV curve. In the IV curve, there are two important points, the I short circuit and the open circuit voltage. At both points, the power generated is zero. Noting that in the PV curve, there are unique points, VPV, IPV, where the power generated is maximum and unique. What are the common faults in PV systems? We have ground fault, line-to-line fault, arc fault, mismatch and shade fault. These type of faults are caused by grouping of cells having non-identical IV curve. And finally, the connectivity fault. Proposed technique. The design technique is based on the analysis of the anomalies appearing in the IV characteristic curve of a PV system. The faults investigated by the proposed technique are mismatch and shady fault, connectivity fault, and short circuit fault. The fault diagnosis will be applied on a PV string composed of 14 PV modules connected in series, and this is the equivalent circuit of a PV module simulated in MATLAB Simulink, which is composed of a current-generated source, a parallel diode, and a series resistance and parallel resistance. Now, how we have developed our algorithm. First, feature extraction. For a fixed operating condition, one fault is implemented in the PV system. This is repeated for different severity of the examined fault in a manner to obtain all possible evolutions of the behavior of the IV curve. The faulty IV curves are compared and examined with the one obtained in normal operation, and finally, the resulting symptoms are identified. Under different fault conditions, we have made the following observations. Here we have take two cases, two irradiation operating condition, 200 watt per meter square, and high irradiation 1000 watt per meter square. In the case of shading fault, we have always a presence of an inflection point. The I short circuit is unchanged, and as the number of shaded cells increases, the VOC decreases. In the case of mismatch RS fault, the I short circuit is unchanged, and the same for the VOC. And as RS increases, the faults become more severe, and there are appearance of an inflection. Mismatch or parallel fault, the I short circuit is unchanged, and as our parallel decreases, the faults become more severe, and the VOC decreases. In the case of connectivity fault, the VOC is unchanged, And as the connector resistance increases, the I short circuit decreases. Finally, with the short circuit fault, the I short circuit is remain unchanged. And as the number of short cells increases, the VOC decreases. So we are able to, we can generate, after this observation, we can generate, we have to identify these symptoms, for analysis symptoms: reduction in the output power, reduction in the open circuit voltage, reduction in the short circuit current, and appearance of an inflection. Now, these symptoms identified will be calculated from the simulated IV curve and are measured in real time. So, from the measurement or from the model, there will be uncertainty in the generation of these symptoms. So, the relative differences between the simulated and the measured differing attribute will be compared with some predefined thresholds. If the symptom calculated exceeds the predetermined threshold, then it will be set 1 as 0 to 0. This signature table was established by looking for each fault the presence or absence of all symptom retained. One fault can generate one or more signatures. Now, let's take an example. In the case of mismatch RS fault, we have two different signatures. The difference here is the appearance of an inflection point when RS increases. Okay, these there are some signatures are common to several faults. Here, F1 has 4 types of faults. F2 and F3 have 2 types of faults. So further analysis is required. In the case F1, discrimination between short circuit and mismatch R parallel and mismatch RS and connectivity fault, here are the type of faults that we will work on. We will zoom on mismatch RS and connectivity fault. Here we can see that it's clear that delta VM is always greater than delta VOC. Using data collected from IV curve during short circuit fault, we have verified that delta VOC is always greater than delta VM. But it's not the case using data in the case of mismatch R parallel fault, where it's not always true. So we are able to discriminate between this type of fault as illustrated here in this flowchart. Case F2, discrimination between short circuit and mismatch or parallel fault. Here we will suppose that we have short circuit fault. Calculate VOC simulated of one cell and the power simulated of one cell, and then calculate the number of short cells expected, which is delta VOC as a VOC simulated of one cell, and the delta V expected will be the number of short cells expected times the power simulated. Okay, if the difference between this power expected and the generated symptoms are close, then it's a short circuit fault as a mismatch or parallel fault. Case F3, discrimination between shading and mismatch RS4. Here we will consider one inflection point. If we have more than one inflection point, then it's a partial shading fault. Here the last part of the graph allow us discrimination between these two types of faults. Now let's calculate Vini using the PV curve, this point, and calculate its image by the IV curve, INI. And calculate the equation D, which is characterized by the 2 points, Vini, INI, and VOC measured 0. And let's take V average, which is equal to VOC measured plus Vini over 2, and calculate its image by the IV curve and the equation D. If the difference between these two currents is close, then it's a mismatch RS fault, as a partial shading. Finally, this flow chart represents the complete algorithm for all cases. Now, simulation and results and discussion. Simulation, in order to test the performance of our algorithm, Simulation of both normal and faulty operation is carried out in MATLAB simulation. The fault detection and diagnosis algorithm take attributes from two simulated 3D systems. The first represents the reality system with different fault modes, and the other represents the normal functioning. Five cases are taken. In each case, we have implemented one type of fault, and we have generated these symptoms. These symptoms will be compared with predefined thresholds corresponding for each case. If these symptoms are greater than this is threshold, then set one as 0. So, and this is the signature date. Noting here the decisions are made correctly, but noting here that is no fault, but we have implement one. Here the problem is the threshold. So we have, if we want to detect this type of fault and it's not severe, we have to change the threshold. Then the decision will become true. Plain cases are taken, but here we have changed the irradiation, a slow irradiation, and also the decision is made correctly. Flexibility of the proposed technique. The system is changed into a PV string composed of 10 PV modules. Another system, each module 1700 watts, and the decision is made correctly for each. As a conclusion, the proposed algorithm is able to detect and identify correctly the fault in the examined PV string. The only limitation is the detection of partial shading fault at low irradiation. Faults with low severity are not detected always. It depends upon the threshold. The CIE is a flexible algorithm. Its accuracy is related to the predetermined threshold. As a perspective, implement intelligent technique to distinguish between SMASH-RS as parallel and connectivity faults, improve the MATLAB code by applying slope change detection, find a maximum technique to determine thresholds, and finally determine the exact magnitude of the connectivity. And finally, thanks very much for your attention.